Okay, welcome to OCR AS Level Physics 2019 Paper 1, Breadth in Physics. Unlike AQA, I can show this on the screen because OCR do allow that. They're a lot more chill than AQA. So multiple choice first. Number 1, which row is correct? Well, strain we know is just the ratio of change in length to original length, so it has no unit, so that can't be right. B, charge, yes, we know it's Coulomb, don't we? Power, no, that's watts. And force constant, well, I assume that means like spring constant. That's not newtons, but newtons per meter. 2, which is the least accurate value for G. Well, we can see the one that's furthest away from the accepted 9.8 is 9.0. So that's furthest away, so it's already least accurate, but it also has the biggest uncertainty as well. So that's the final nail in the coffin for it. The answer's A. 3, where is the most compression? Well, I mean, you can answer this without really even knowing any physics. You know that if you bend something, then it's going to snap on the far side. So it would snap at C. So that's where the most extension is happening. So it stands to reason then that the bit on the other side at B are going to be squashed the most. So yes, it's B. 4, we have a force time graph. Which statement is not correct? So A, the area under the graph is equal to the work done. We already know that's not true because we know area under a force time graph gives us impulse or change in momentum. So that's our answer, A. Let's just check the other ones. B, max acceleration in the middle. Yes, because we have the biggest force. C, the area under the graph is impulse. We just said that has to be true. And D, it has the units kilogram meters per second. Yes, that's true because of course it's mass times velocity. 5, what do we have here? We have a couple. Force at each nozzle is 0.12 newtons, perpendicular distance is 0.082 meters. So what's the work done by the forces as it does one complete revolution? Well, work done is force times distance. I like calling it E. Okay, maybe sometimes W. I switch between the two, but it is an energy ultimately. So we take our force, there's two forces, so that's 0.24 newtons, and we times that by the distance. One complete revolution, well, they're doing that work over one circumference, so that's pi d, so that's our 0.082 times pi. And that gives us 0.0618 joules, so the answer is D. 6, which circuit can be used to monitor the variation of light intensity? Well, A has an LED, so it can't be that. B has a variable resistor, can't be that. C, that is an LDR, so that's a light dependent resistor, that's what we can use. D is a thermistor, no, that's going to be to do with temperature. 7, lots of information here, so what do we have? So we're changing all our 60 watt bulbs for 12 watt bulbs. There's 10 of them, okay, so we're going from 600 watts to 120 watts. Each bulb can be used for 2,000 hours in 1 year. Okay, so let's first of all figure out how many kilowatt hours are used per hour. So for 600 watts, that's going to be 0.6 kilowatt hours because, well, it's 0.6 kilowatts, times that by 1 hour. For the 120 watt bulbs, that's 0.12 kilowatt hours. So then we times that by 2,000. We end up with 1,200 kilowatt hours per year for the Beastie bulbs, 240 for the LED bulbs. So therefore our saving is just going to be the difference between those two times the price of 1 kilowatt hour. Obviously that needs to be in pounds, and that gives us £147.84. So the answer is C. Not a really easy one, that. 8, we have a force, and we have an angle theta, and we have a distance, and we have work done. What's the angle? Well, we know that work done is force times distance, but that's only if the force and distance are parallel to each other. So if they're at an angle, then we times by cos of that angle, so FD cos theta. So rearranging, cos theta is work done over force times distance. Yes, I've changed the W here, sue me. So that's 52 divided by 12 times 9.6. And so inverse cosing that, and we get 63 degrees. So the answer is C. Nice easy one. Now we have a wire, and it's got 3 ohms resistance. We stretch it so it's half as long again, but the volume remains the same. Not a super easy one, but let's write down our resistivity equation. So R equals rho L over A. Now, rho is staying the same because it's the same material, so we can say that R is proportional to L over A. However, how are they changing? Let's look at volume. Volume is equal to length times area. So therefore, if length goes up, then area has to go down. So that means that if R is proportional to L over A, L is going up by 1.5, factor of, that is. Area is going down by a factor of 1.5, so that means that the whole thing is going up by a factor of 1.5 squared. So that gives us a new resistance of 6.75 ohms. The answer is D. 10, okay, we have this potential divider circuit. So the variable resistor goes from 0 to 3R, but R is the fixed resistor. We have the total voltage, that's the EMF. So we're going from the minimum to maximum value. So basically, what's happening to the voltage across the variable resistor. Fairly easy. We know that first of all, just from V equals IR, if there's no resistance, then there's obviously not going to be a voltage. There's no energy being lost across the variable resistor. So it has to be from 0 volts, so it's either A or B. What's it going to? Well, when we have 3R compared to 1R for the fixed resistor, we know that the voltage is shared accordingly, proportional to the resistance. Bigger resistance, bigger share of the voltage. So there's 4 volts available altogether, therefore that's split into 3 volts for the variable resistor and 1 volt for the fixed resistor. So the answer is B. 11, we have 2 waves. They're in phase when they leave. So what distances give constructive interference at point Z? Well, we know that they need to be in phase at Z, and because they've traveled different distances, it's all about that path difference. And if they're arriving in phase, then the path difference needs to be a multiple of the wavelength, in other words, n lambda. So we know that the wavelength is 10 centimeters, therefore we need a difference between these distances that is a multiple of 10. 60 to 75, that's 15, so that's not 1. 75 to 95, yes, that is. It's 20. C is 25. D, that's 35. So actually for A, C, and D, they'd arrive completely out of phase, so there'd be destructive interference in those cases. 12, which one has the smallest critical angle? You could probably guess this, to be honest, but let's prove it. Let's start off with Snell's law. I always like to start off with it. So n1 sine theta 1 equals n2 sine theta 2. We don't know what n2 is, but that doesn't matter because, well, it's just relative, isn't it? We're just looking for the smallest critical angle. So therefore, we can just get rid of n2 and sine theta 2. And of course, sine theta 2 disappears because we're talking about sine of 90. So that means that n sine theta c is equal to some constant. We can just call that 1 if we're talking about air. So therefore, rearranging that, we just have n is proportional to 1 over sine theta c. Therefore, smallest critical angle equals biggest refractive index. So the answer is A. 13, we have a frictional force. So the force is directly proportional to the speed squared. So therefore, we can say that F is proportional to V squared. So what's the relationship between the power, well, rate of work done against frictional force? Why don't they just say power developed? Whatever. And the speed V of the object. Okay, so let's write down our equation for power developed. P is equal to FV, force times velocity and force times speed. Pop in our new equation from above into there. We find that P is proportional to V squared times V, so in other words, proportional to V cubed. So the answer is D. 14, we have a particle accelerator. We have a PD of 120 kilovolts, and the current is 8 microamps. What's the total energy transferred in 2 hours? Okay, so let's find out what the time is in seconds first. It's just 2 hours times 3,600, so that gives us 7,200 seconds. We know that energy is equal to power times time. Can we get power? Yes, we can, from voltage times current. Therefore, energy is equal to just VIT times those all together, and that gives us 6,912 joules, so the answer to 2 sig figs is D. 15, we have an electric charge that is quantized and a multiple of the elementary charge. Which charge is possible? So we know the smallest charge possible is 1.6 times 10 to the minus 19. That's the charge of an electron. Okay, quarks can have a third or 2/3, but we're not concerned with that here. So 1 times 10 to the minus 19, not a factor. 4 times 10 to the minus 19, not a factor. 8, yes it is, because 5 lots of 1.6 is 8. So therefore the charge is 5 lots of E. So C is the answer. 16, we have 2 forces. Which diagram shows the resultant force? Well, we know that to find a resultant, all we do is add vectors top to tail. So I'll just move the one from the right to the left, and we end up with a line straight down. So the answer is A. 17, power has the base units that. What are the base units for intensity? Well, intensity is equal to power divided by area. So that's kilogram meter squared per second cubed divided by meter squared. So that just cancels out the meter squared, and we just end up with kilogram seconds to the minus 3. So the answer is A. Okay, what do we have? A ball of diameter that is held above the ground. The bottom of the ball is 10.2 centimeters above the ground. Blah, 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 blah. What's the time taken for the ball to reach the ground? Okay. I feel like they're giving us too much information, but let's have a look at this. SUVAT. So we have S, that's our 10.2, U is 0, A is 9.8, and we're looking for T. Now, lots of people get, oh, you need to put minus 9.8. It doesn't matter, kiddos, because we're only dealing with the downwards direction here. It would be a different case if we had something going up and then down, for example. So we're going to use s equals ut plus half at squared, and yeah, we don't need to do anything with that 2.5 because, well, the bottom of the ball is 10.2 centimeters away from the ground and the bottom of the ball hits that, so that is our displacement. So they're trying to catch us out there by giving us the diameter. So you might be tempted to like add on the radius or something like that. Not the case. So rearranging that, time is equal to the square root of 2s over a, so we end up with 0.144 seconds. The answer is B. 19. Which wave can be polarized and has a typical wavelength of about a few centimeters? Well, sound can't be polarized because it's longitudinal. The rest are EM, so they can. Visible light we know is around hundreds of nanometers or times 10 to the minus 7, so it's not that. Ultraviolet's even shorter again, so therefore it has to be microwaves. 20. Stationary waves in a tube. One thing you need to know about them is that at a closed end we have a node, at an open end we have an antinode. So the only one that's correct there is C. Okay, normal questions. 21. What's the other condition needed for a system to be in equilibrium? Well, it's not only no forces, but also no turning forces. So resultant torque must be 0. We can also say resultant moment must be 0. Or we might say, you know, sum of clockwise moments equals sum of anti-clockwise moments, but that's a long way of putting it. No resultant torque is all good. All right, we have the ball with the weight and the normal reaction force from the table. So what's the object that experiences a force of magnitude W but in the opposite direction to W? You might be tempted to say the table, but no, that's not true. Now, Newton's third law is always true, whether or not an object is stationary or it's falling through the air or whatever. So even if this ball was falling, it would still be true. Where is the equal and opposite force? Well, what is pulling the ball down? It's the weight, the force of gravity from the Earth. So therefore, what's equal and opposite to that? Just flip it on its head. The ball is also pulling up the Earth with the same force. Next bit. According to the student, W equals N is a consequence of Newton's third law of motion. Why is it incorrect? Well, we just sort of said that, haven't we? But when it comes to balance forces, so that there's no acceleration, that's to do with the first law. But the more important thing is that when it comes to Newton's third law, the forces have to be the same type. So force of gravity equal and opposite to a force of gravity. Reaction force equal to a reaction force. You get the idea. So we have this dolphin, and we're being asked to find what the overall upwards force is due to the tensions. So we need the vertical components pulling upwards. So let's look at the left one first. So we have 68 newtons. We know it's going to be smaller than that because 68 is our resultant there. So we're going to be timesing by sine or cos. But is it going to be sine or cos? We times by sine because we're turning away from that 10 degrees to get to the vertical component. So we times by sine of 10 degrees. If you don't know what I'm talking about, have a look at my easy vectors trick video. Very useful. Much better than dealing with triangles. What about the other one? Well, it's 87.4 times, but can you see we're going through the 50 degrees now to go from the 87.4 newtons to the vertical, so therefore we times by cos instead. Adding those up, we end up with 68.0 newtons. And the mark scheme, weirdly enough, says 68 sine 10 or 87.4 cos 50, whereas what it really should say is plus, so they've kind of got the mark scheme wrong there. So being asked to find out the mass, well, we know that 68 newtons are pulling upwards due to the tensions, so that's balancing the weight of the dolphin. Weight is equal to mg, so mass is equal to weight divided by g, so that's 68 divided by 9.81, and we end up with 6.93 kilograms. Next, we're being asked to calculate the ratio of extension of B to extension of A. So we have the same length and same cross-sectional area, but we have different Young modulus and of course force as well because we know the tensions are different. So let's write down the Young modulus equation. E is equal to FL over A delta L, and we know that L and A are staying the same, so let's cross those out, and so we now have a proportionality equation. Delta L is proportional to force, tension in this case, divided by the Young modulus. So what we can say then is delta L of A divided by delta L of B, because that's what we want ultimately, is F divided by E for A divided by F divided by E for B. Some people get a bit confused when dividing fractions, but remember that if you divide by a fraction, it's the same thing as timesing by the reciprocal. So we end up with FAEB over FBEA. Putting the numbers in, we have 68 newtons divided by 87.4 newtons, and then we're timesing that by 1.29 divided by 1, because, you know, it's just 1E for A. So we can just cross that out, and we end up with exactly 1.00. Well, that's a bit convenient, isn't it? That's not a given, that's just the way that the question has gone. 22, we have this metal ball. It falls vertically. Now we have this graph and it looks like it's moving sideways, doesn't it? But just remember, it is just falling vertically. The x-axis here is time, not distance. So we have the time it takes to hit the ground. We have a collision time. Interesting, there we go. So chances are we're going to have to do force is equal to rate of change of momentum at some point. And we have the mass as well. First things first, describe and explain the variation of velocity. Well, okay, a bit of a weird question, but it accelerates downwards due to gravity. At 0.5 seconds, the reaction force or normal force from the ground provides impulse to the ball, changing its momentum and direction. What else can we write? Well, the mark scheme says you can write down velocity is equal to gradient, but that's not really describing. Maybe that is explaining, I don't know. But that's how we can tell what the velocity is. I don't like this question. So B, we're being asked to use SUVAT to find out what the velocity is just before it hits the ground. So what can we know then? We know S is 1. I don't know. It's a bit hard to read. So that's 1.3 in the middle. So that's 1.24 there. So I'm going to say it's just below that. So let's say 1.23. Could have given us a nicer number there. U is 0. V we're looking for. A is 9.8 again. Again, we do not need to use minuses. We would do if we were looking at it going up and coming back down. So we're going to use V equals U plus AT. U disappears. So V is just 9.81 times 0.5. Easy peasy. That gives us, I'm just going to say 4.9. Next we're being asked to draw a tangent to show the rebound speed. Okay, so we just draw a tangent. I don't have a ruler. You always must do it with a ruler. Make yourself a big triangle and just do change in Y divided by change in X, or in other words, change in S divided by change in T here. And that should give you about 3.5. Okay, D, calculate the average resultant force. There we go. So we are going to have to use force is equal to rate of change in momentum. So delta mv divided by T. T is not the time of flight, but the collision time, impact time in this case. So mass of 0.056 kilograms times, well, what's the speed? Well, we're looking for a change in speed here, aren't we? Because, well, the mass isn't changing, so we're looking for delta V. Well, this is where we do have to be careful with our pluses and minuses because we're going down and then up. So we're going down at 4.9 meters per second, but up at 3.5. Doesn't matter which way around you do these, so long as you do one the opposite to the other. So we're going to say the difference is 4.9 take away minus 3.5, because we're going all the way from 4.9 meters per second through 0 to minus 3.5. Obviously our change in velocity is going to be greater than just 4.9. Divide that by the collision time, 1.8 times 10 to the minus 3 seconds, because it's milliseconds, and it gives us a force of 261 newtons. Let's do that to two sig figs, 260 newtons. 23, we have a cell, and we have an internal resistance, so that's little r, and we have an EMF of 1.4 volts, that's epsilon. We have the resistance of A, and, well, basically we can find out the resistance of B, so let's do that first. 9.5 ohms per meter, times that by 0.4 meters, and it gives us 3.8 ohms. Okay, so we've been asked to find the current in the circuit, so we know that internal resistance equation EMF is equal to IR plus IR, so that's just current times total resistance, so that's load resistance plus the internal resistance. It's just V equals IR, just in a different form. So we need to know what the total resistance of the circuit is. So let's find out what the resistance of A and B is first. I'm just going to call it 1 over R total. So 1 over R total is equal to 1 over 1.8 plus 1 over 3.8. It's always a good idea to do the right hand side, then press equals, then do 1 divided by the answer. That gives us 1.22 ohms. Okay, so we have the resistance of big R now in our equation. And well, we can just say V is equal to IR, it's the same thing like I said. So current is equal to V over R, so that's 1.4 volts altogether, divided by our total resistance of the circuit of 1.22 plus the 0.62. And that gives us a current of 0.76 amps. Okay, so next we're being asked to calculate the ratio of power dissipated by internal resistance divided by total power supplied by the cell. Right, power dissipated due to resistance is equal to I squared R, and power supplied by cell is V times I. I'm just going to call those P1 and P2. So P1 divided by P2 is I squared. Oh, flip, I should have put little r, sorry about that, because we're talking about internal resistance. And then divide that by VI. One of the i's cancels, so we end up with I little r divided by V. I should probably replace that with epsilon, to be honest, seeing that we're talking about the EMF. So I times R, so that's 0.76 times our internal resistance of 0.62 divided by the EMF of 1.4. And that gives us a ratio of 0.337 to 2 sig figs. We'll call that 0.34. Okay, we have the VI graph for some lamps. And what are we being asked here? We have them in series and then parallel. We're being asked, why is the current in P almost 3 times greater than in S? Well, we know it's to do with the fact that two resistors, or lamps in this case, in parallel give you a lower resistance than if they were in series. But we need to take into account the graph above. So let's have a look at the series circuit first. We know that each of these bulbs, because they're in series, gets 3 volts. Let's have a look at the graph. 3 volts corresponds to 0.36 amps going through each of them. And they're in series, so they have the same current, of course, don't they? Parallel, we know that they both get 6 volts, and so that's right at the top of the graph. So 6 volts corresponds to 0.5 amps. So they get 0.5 amps each, and so that means that the total current in the circuit has to be 1 amp. So there we go, almost 3 times greater. Let's just prove that. 1 divided by 0.36 gives us 2.8 times greater. 24. Oh, great long answer question. I hate these. How are we going to get the refractive index of a block? Well, we put it on a piece of paper, draw around the block, we draw a normal 90 degrees to the surface, we get a ray box, shine the light in at an angle, and then we put dots to mark where it went in and where it comes out, and then we can join up the dots afterwards to measure the angles between the normal and the incident ray and the refracted ray, and that should give us theta 1 and theta 2, or we can call them I and R. So refractive index is equal to sine I over sine R, or sine theta 1 over sine theta 2. We could get it just from one result, but a better thing to do is to change or vary the angle of the incident ray, let's say for 8 different angles. And then we're going to plot a graph of sine I versus sine R, and we'll end up with a nice straight line, hopefully. The line of best fit, the gradient of that will give us the refractive index. Okay, B, we have a loudspeaker. And we have station waves being set up, and then we're using a microphone. It's measuring where the nodes are, so that means that there's no energy there. So it's going to be quiet on the microphone. Not that we care too much about that. So let's have a look at this graph. F against 1 over L. So draw a straight line of best fit, determine the gradient of the line. Easy peasy. You should get about 170. Next, why is the gradient of the line V over 2, where V is the speed of sound? Well, let's have a look at what our axes are. We have F against 1 over L. Let's just have a think. Let's draw what the stationary wave looks like. We know the distance between nodes is not a full wavelength. It's half a wavelength, isn't it? So we know the gradient is equal to F over 1 over L. So that's the same as F times L. But we just said that the distance L between nodes is half a wavelength. So L is equal to lambda over 2. Putting those together, we can say that the gradient is equal to F times lambda over 2. Therefore, because V is equal to F lambda, that means that V is equal to 2 times the gradient. And then we're being asked to find out actually what the value is. We just take our gradient, 170 times by 2, 340 meters per second. Sounds about right. Lastly, smaller values of L are much more difficult to determine and produces a large uncertainty in values of 1 over L. How could the percentage uncertainty be reduced? Well, we could use a longer wavelength, couldn't we? Because that will result in bigger lengths of L, and that's a lower frequency as well. Therefore, we'll end up with a smaller percentage uncertainty in L. 25. State one piece of evidence for the wave-like behavior of electrons. Well, the only one really is electron diffraction. B, in electron gun, we have a max kinetic energy of 210 electron volts. So the final speed of each electron is 9 times 10 to the 6 meters per second. There's a couple of ways you can go about this, but obviously 210 electron volts. Each electron volt is 1.6 times 10 to the minus 19 joules. But it's worth remembering that when we have an electron that's accelerated through 210 volts, its energy ends up being 210 electron volts. That's literally all that means. So we can say that the energy of the electron, I'm just going to call that EV, is equal to half mv squared, because the energy supplied is being turned into kinetic energy, as it were. I'll probably get told off by several people for saying that. I don't care. So rearranging that, we can say that 2 lots of the energy divided by the mass is equal to v squared. We end up with a velocity of 8.6 times 10 to the 6 meters per second. Next, calculate the de Broglie or de Broglie wavelength. Let's get our equation out. Lambda is equal to h over p, or h over mv. So that's Planck's constant divided by the mass of an electron times the speed that we just calculated. And I think I can tidy up some powers of 10 here if I want to be smart. You don't have to be though. and that gives me 8.47 times 10 to the minus 11 meters. Let's go with 8.5 to 2 sig figs. C. EM waves interact with matter as photons. Explain the photoelectric effect using ideas of photons, conservation of energy, and work function. Nice easy question really to finish off. As far as righty questions go, an electron on the surface of a metal requires energy to be liberated. The minimum energy required to do this for a specific metal is called the work function. How does this happen? Well, an electron can absorb a photon to obtain this energy. If the energy absorbed is greater than the work function, phi, the excess energy is converted. Again, I might get told off for saying that, but we all know what that means. So let's stop splitting hairs. The excess energy is converted into kinetic energy of the electron, of course, because energy has to be conserved. The excess energy can't just disappear into thin air. So there we go. Hope you found that helpful. If you did, please leave a like. If you want to see other OCR papers, then click on the card and it'll take you to the playlist. Bye for now.